Okay, so today we talk on optimization of functions of several variables. So if we are given a function of more than one variables defined on some open set, then how we can find out its local maximum, local minimum, or in some region, how we can find out the absolute maximum value of f or the absolute minimum value of f. Let us recall in the case of one variable what happens, how do we determine whether f has local maximum or local minimum at a point a, and we are going to see similar condition. That means we shall write a theorem, and when it is restricted to one variable case we are going to get the same. So first we are writing condition for, means at a point when do we get local maximum or local minimum of a function of one variable. So you must be knowing this. Let f be differentiable on an open interval I, and let a in I be such that, or a in I satisfy f dash of a equal to 0. Such points are also called critical points of f, or they are also called stationary points of f. Critical points, yes. Okay, so the first one, if we are assuming that f is 2 times differentiable, right? If the second derivative of f at a is less than 0, then f has local maximum at a. This is known to us. And similarly, if f double dash of a, that means the value of the second derivative of f at a is positive, then f has a, you can write f has a, because at more than one point a function have or may have local maximum or local minimum, then f has a local minimum. At the point a. As I said, we are going to derive similar condition. So before going to that condition, we shall require some preliminaries. So that first we now discuss, and we shall require bilinear forms and or bilinear maps and quadratic maps. So that first we are defining. So first definition, let V be a real vector space, means it is a vector space over the field of real numbers. Right. A map f from V cross V to R is called a bilinear map. Bilinear map if the following conditions hold. If the following conditions hold. The first one, f uv. It is same as f v u for all uv in the vector space v. Means f is symmetric. The second one is f of u plus v w. It is same as f of u w plus f of v w for all u v w in v. And the third condition says f of alpha u v, that is same as alpha times f of u v. It is true for all u v in v and alpha real. Alpha is a scalar. So now by using conditions 2 and 3, one may deduce that the function f is linear in the first coordinate. And because of the symmetry, the first condition, it follows that f is linear in both the variables. Right? Okay, so now first our task is to determine what are all bilinear maps on Rn. So now we give a characterization. So we have a theorem. Right. A map f from Rn cross Rn to R is a bilinear map if and only if there exist scalars, means real numbers, aij n squared real numbers, such that aij equal to aji for all I and j, and f has the form f of x1 x2 up to xn, y1 y2 up to yn equal to summation I from 1 to n, summation j from 1 to n, aij xi yj for all x1 x2 xn y1 y2 yn in Rn. Right. Let us again read the statement of the theorem. It says what? A map f from Rn cross Rn to R is a bilinear map if and only if we get n squared scalars aij, such that what? Aij is aji for all I and j, and f has the form, means fxy or f of x1 to xn, y1 up to yn, that is same as summation I from 1 to n, summation j from 1 to n, aij xi yj. Okay, so first we are going to assume that f has this form with aij equals aji, then we show that f is bilinear map. In fact, that is much easier task. So assume that f has the above form. Let us start with any x bar equal to x1, xn, y bar is y1 up to yn. Let us take any two elements of R, n. N is a natural number, right? Then that is fixed. Right. Then f of x bar, y bar, that is by definition summation I from 1 to n, summation j from 1 to n, aij xi yj. But it is known to us that aij is same as aji, and because it's a finite sum, it is taken in any order is going to give us the same sum. So it is same as summation j from 1 to n, summation I from 1 to n. In place of aij now we are writing aji, and we may write in this form yj xi, and that is same as f of y bar x bar. Means we have shown that f is symmetric. Right. Let x bar, y bar, z bar be elements of Rn. Right. Then f of x bar plus y bar z bar, it will be by definition, or because we are given what is the form of f, so I from 1 to n, summation j from 1 to n, aij xi yj, means here we are going to get xi plus yi zj, and this is same as, now we may separate them, so that is same as summation, we may write this form to ij from 1 to n, aij xi zj plus summation ij, both are running from 1 to n, aij yizg, and that gives f of x bar z bar plus f of y bar z bar. Right. And similarly, now you can show that I'm living, so you can just prove it. You need to prove, that is much simpler. Prove that f of alpha x bar y bar, it is same as alpha times f x bar y bar for all x bar y bar in Rn and real alpha. Right. So if f has the given form, means yes, with the condition that aij is aji for all I in j, then we have shown that f is a bilinear map. Now we prove the converse. Right. Now assume that f is a bilinear map, that we are assuming. let E1, E2 up to En be the standard basis of Rn. That means E1 is what? It is n tuple for which the first coordinate is 1, the rest are 0. E2 means the second coordinate is 1, the rest coordinates are 0. Then it is known to us that it's a basis and it is called standard basis for the vector space Rn. So now we define Aij. So for 1 less than or equal to ij less than or equal to n, define Aij equals f of Ei Eg. And what is our assumption? Our assumption is that f is a bilinear map, means f is symmetric. So since f is a bilinear map, what we are going to get, Aij equals Aj for all I and j. So now our task is to show that f is linear in the first coordinate, and then we are done. So let us do it. Let x bar, y bar, z bar. No, I'm sorry. What do we want to show? Yes, f has this form. That is what we want to show. I'm sorry. So we start with let x bar, y bar in Rn. Right. Then f of x bar, y bar, it is f of, now because x bar is what? x1, x2 up to xn, and even up to n is a standard basis for Rn, so we can write this as summation I from 1 to n xi ei, and we can write y bar as summation j from 1 to n yj ej. Right, and now because f is linear in the first coordinate, this is going to give us summation I from 1 to n xi f of ei summation j from 1 to n yj ej. Right, and we have already observed that f is also linear in the second coordinate. So by using that fact, we get summation I from 1 to n xi, then one may write summation j from 1 to n yj f of ei ej, right? But f of ei ej is aij, so this sum can be written in the form summation I from 1 to n summation j from 1 to n aij xi yj. And so this finishes the proof. So we proved both the sides. If f has the given form, then f is a bilinear map on Rn, obviously, and if f is a bilinear map on Rn, then f has this form. So now we define what is mean by a quadratic form or quadratic map. Definition: let V be a real vector space. A map G from Rn to R is called a quadratic form. It is called a quadratic form. If there exists or there is a bilinear map G, no, not G, F on Rn, means f is a function from Rn cross Rn to R. If there is a bilinear map f on Rn such that, I made a mistake, I should write, that is my mistake, a map G from V to R. A map G from V to R is called a quadratic form if there exists a bilinear map on V, means f is a mapping from V cross V to R, such that G of V equal to f of V for all V in V. Again, V is a real vector space and G is a function from V to R. Then G is called a quadratic form if we get a bilinear map f on V such that G of V equals f of V for all V in V. Right? Now I am giving you one exercise and that can be done by using the above theorem. So exercise: show that a map G from Rn to R is a quadratic form if and only if there exist scalars, means real numbers a, I, j, there are n squared such real numbers such that a, I, j equals a, j, I for all I and j, and G has the form that I am writing, and G of x1, x2 up to xn equals summation I, j, both of them are running from 1 to n, a, I, j, x, I, x, j for all x1, x2 to xn in Rn. Right, again I tell you how you will be able to prove it. Just use this theorem and use this definition, because in definition itself says that a map G from V to R is a quadratic form if and only if there exists a bilinear map F, so that G of V is FVV, and already we have identified what are all bilinear maps on Rn. Right. So once we see a quadratic form, if we are given a quadratic form on Rn, we can associate a n cross n real symmetric matrix, namely Aij, and conversely also. So that I am writing first. So if G is a quadratic form on Rn, then we get n cross n real symmetric matrix, namely Aij. And conversely also, if we are given a real symmetric n cross n matrix, then by using that we may define G by this way. So in fact such Aij we are getting from G, that is, or those numbers are unique. So given a quadratic form on Rn, we may correspond or we may assign a real symmetric matrix, n cross n real symmetric matrix with a quadratic form G, and conversely if we are given an n cross n real symmetric matrix, then we are able to find out a unique quadratic form. So there is a one-to-one correspondence between the set of all quadratic forms on Rn and the collection of all n cross n real symmetric matrices. Right? We shall soon see what is in fact the relation between these two. Right? You people must be knowing what is the inner product on Rn. Means if you are given two elements x1 up to xn, y1 up to yn, then their inner product x1 up to xn, y1 up to yn, that is defined by x1 y1 plus x2 y2 up to xn yn. That is known to us. And also it is known to us that if we are given any n cross n matrix, then it defines a linear operator or linear map on Rn. Right. Okay. So that I'm writing now. I'm writing how we are associating this real symmetric matrix with a quadratic form. So let G be a quadratic form on Rn, and let capital A equals Aij be the n cross n real symmetric matrix associated with G. Right. Now you can check that if x bar. Now we are going to write elements of Rn as a column vector. So first एक बार मैं लिख देता हूँ. I'm not going to write every time. If x1, x2 up to xn is an element of Rn, then you can check that it's an easy exercise that g of x bar is nothing but inner product of a x bar with x, or you can also check that this is nothing but x bar transpose a x bar. Right? Just use the form. See what is A is Aij. Just take the usual matrix multiplication. How we take the matrix multiplication of an n cross n matrix with n cross 1 matrix, right? And we take its inner product with x bar. X bar means x1 up to xn. Then we are going to get the form summation ij from 1 to n aij xi xj. So this is the way. So what we have shown, if G is a quadratic form on Rn, then we get a unique n cross n real symmetric matrix, so that G of x is nothing but inner product of Ax with x. And conversely, if we are given any n cross n real symmetric matrix A, then we define Gx to be inner product of Ax with x. Then you can check that G is a quadratic form. Right, so this is a characterization, or it is a form of a quadratic form on Rn. Right. Now we note some facts. First, it is very well known that if A is an n cross n, or if A is a square matrix which is real and symmetric, then all its eigenvalues are real. That is known to us. So now we give some definition. When do we call a matrix to be positive definite, negative definite, and then we shall state some relation between that quadratic form and the matrix A. Okay, so definition. Let A, or let me just call it G. In fact दोनों के लिए सेम ही होता है. So let me just give the definition for A. Let capital A be an n cross n real symmetric matrix. The first one. Then A is called positive definite. If what? If the inner product of A x bar with x bar is strictly positive. Here some people write it in this form too. X bar transpose A x bar is strictly positive for all non-zero x bar in Rn. See, if we take x bar to be 0, then obviously, because A is a linear map, we are going to get the first vector to be 0, and as soon as you get a vector to be 0, then its inner product with any other vector will be 0. The second one, A is called negative definite. If what? Same way, x bar transpose A x bar equal to inner product of Ax bar with x bar is less than 0. Here again I am saying, here we are using the usual inner product of Rn. It is less than 0 for all non-zero x bar in Rn. See, we have defined this for a real symmetric matrix A, but we can also define it for a quadratic form. That means if we are given a quadratic form G, then we may associate a real symmetric matrix A so that Gx is Axx. That means if we are given a quadratic form on Rn, we say that G is positive definite if what? G of x is greater than 0 for all non-zero x, right? By the same way we say that G is negative definite form if what? G of x is less than 0 for all non-zero x. So either we define for an n cross n real symmetric matrix or we define for a quadratic form, they are one and the same. Again I say G is a quadratic form, so we may associate a unique real symmetric matrix A. So we say that, or it is defined this way, G is called positive definite quadratic form if G of x is greater than 0 for all non-zero x. G is called a negative definite. It is already a quadratic form. G is called negative definite if G of x is less than 0 for all non-zero x. Okay, and I am writing the following fact that must be probably known to you. So let A be n cross n real symmetric matrix. Then the following statements hold. The first one is positive definite. This is going to happen if and only if all the eigenvalues of A are positive. And the second one is a similar result, is negative definite if and only if all the eigenvalues of A are negative. Here we can also replace A by quadratic form G. So we can say that G is a positive definite quadratic form if and only if all the eigenvalues of the matrix associated with G are positive, and the same thing can be done for the second one. See, people also define what is mean by positive semi-definite. We have defined positive definite. One can define this way: A is called positive semi-definite if what? Inner product of Ax bar with x bar is greater than or equal to 0, and there we don't need to put this condition, right? Again, A is called positive semi-definite if for every x in Rn we have inner product of Ax with x greater than or equal to 0. By the same way you can define negative definite, and here you may also add two results, namely A is positive semi-definite if and only if all the eigenvalues of A are non-negative. and by the same way A is negative semi-definite if and only if all the eigenvalues of A are non-positive. So we stop here. We continue this in the next lecture. Thank you.